Hello and good morning. Today is Sunday, August 8th, 2021. Since I only have limited time to do all that I have to do, I'm going to experiment for a little while with the idea of a video journal when and where I can. I'm going to document what we're developing and also a bit about my personal life. That's because what we develop, I intend what we develop, what I develop, what develops here, to be the intellectual property that empowers a company. And as that company grows, I intend its growth and its success to empower inventors. So it seems appropriate to document some of my life as an inventor. This is why it is so important. If you know any inventors who are truly dedicated to their craft, then you know some crazy people. Maybe. I feel like a crazy people sometimes, for sure. If only because it's unusual. Most people don't do this. So that makes me one of a minority. And we'll start from there. I can go ahead and show you a machine called what we call the reference machine. It'll fit inside a ring of ferrite that looks like this. Maybe we can grab our other camera. Yeah, there we go. Hi! Here's a ring of ferrite. I like these. I have a bunch of them, and it's an iron oxide that has extremely low magnetic loss. So we're going to build a motor inside this ring. This is the outer ring, and inside there will be some coils and spinning parts. As you see on the screen here, on the main screen in sort of rainbow color, we have an outer ring in our model that is representing that ferrite ring. So I just turned it green, and the software highlighted it for us. And on the inside, we see that there are some ordinary and fairly conventional ceramic magnets. So we'll put that on the camera. These are kind of dime a dozen. The one I'm holding is not. It's made of barium ferrite. But the strontium ferrite ones are very common. And this is somehow a sort of a grandfather geometry, a little less than 1 by 2 inches. If we take these easily obtainable and inexpensive magnets and print a hexagonal rotor, along with some windings, we can make a machine that generates no energy at all, or I should say harvests no energy at all, and also stows no energy at all, meaning it's a exactly conventional electric machine. Now, ordinary motors and generators, like we might get in a generator at Harbor Freight to power our house when the power is out, or a motor in an electric toy. These don't harvest energy from the ambient environment at all. They only convert electrical and mechanical energy. They're a trading post. They trade one for the other. And they'll lose some energy on the way. For example, the windings will be made of copper, and copper is a resistor. It's a metal with electrical resistance. So it will lose some energy. It's a heater. As current flows through the copper, it will heat up the copper. So not only do we have electrical and mechanical energy in play, but we also have thermal energy in play. Our generator, our motor, creates some thermal energy, some heat, as it is running. So if we're asking a generator to turn 1 horsepower into its electrical equivalent of 748 watts, because electricity has, well, that's the conversion ratio. 1 horsepower equals 748 watts. We might run that generator at 1 horsepower from a gasoline engine or a turbine or something. But if we put in exactly 1 horsepower, we're not going to get out 748 watts. We might get out 720 and find that the missing 28 watts is appearing in the form of 28 watts worth of thermal energy, heat, in the copper windings and the other structures of the physical generator. That's pretty widely known. But even if that generator were perfect and it had no other losses, if we put in 1 horsepower, we could only ever draw out 748 watts of electricity. So all it is a trading post. It can't harvest energy from the ambient world around it for free. It can only convert mechanical energy that we apply deliberately into electricity. Well, that's not a problem, but it is the state of the art, even as of 2021. I mean, in terms of how we generate electricity on this planet, right? If we have a hydroelectric dam or a coal-fired power plant, well, that's why we have to burn so much coal. That's why the dam has to be so large and create a river behind it, or a lake behind it. I'm thinking of Lake Roosevelt here in Washington State. Behind the Grand Coulee Dam. It requires a lot of force to generate that much mechanical energy and convert it to that much electrical energy. What we're looking at here on screen, I call the reference machine. And this is a pretty radical new technology, although it seems very ordinary at first, because all it is an electrical machine. Now, if we have a machine that can act as a motor and turn electricity into mechanical power just as well, or just as ably as it can act as a generator, turning mechanical power into electrical power, then we call it an electrical machine. It can trade either way, mechanical, electrical, who cares? So this reference machine has a special way of operating in which we can eliminate the losses, in other words, the heating of the copper from its measurement. So it's like a watt meter. When we spin it, it will tell us exactly how much electrical and mechanical energy it is dealing with. So unlike an ordinary electrical machine, which is losing some energy to heat, and we don't quite know how much because we'd have to use a thermometer and a bunch of physics and da-da-da, our reference machine has a display on it that reads precisely how much mechanical energy and how much electrical energy it is providing or consuming. It is like the watt meter or the electric meter on your house. It's there to be very precise in how it measures because energy is money. We apply that principle here, using a rather novel technique, I would presume, so that if we apply 1 horsepower worth of electricity to our reference machine, we can also measure that it's yielding exactly 1 horsepower of mechanical energy. All the losses occur on a separate line item. So it allows us to observe mechanical energy directly. And this is very important because we're building generators that really play with those constants. We'll get into it a little bit more later. But what I will show you now is our post-processing software. It's only a spreadsheet written in Excel right now, and it is evaluating the performance of our reference machine. Now in this software, if we look at some of our really novel technologies, for example, I'll show you this. You can see that there are some dark lines and light lines and ziggy-zaggy lines and all kinds of stuff going on, because this is one of our breakthrough technologies that is harvesting energy from the ambient environment. Our computer models tell us this is possible, and our physical research tell us that this is possible. We may be the first to legitimately do it, and by that I mean put it on the market without going crazy in the meantime. We can see here though that if I highlight on the chart for you the circuit energy in this dark orange trace and the mechanical energy in this light orange trace, you can see that the two curves do not overlap over certain portions of the cycle. In other portions they do overlap and we only see one curve. But in other portions there is no overlap. There's a distance between them, a difference. And this gives us the ability to harvest energy from the ambient environment. if these two curves overlap at all times, if they always superimpose, then there's never any difference between mechanical and electrical energy. And all we have is an electrical machine, just a trading post converting one to the other, but harvesting nothing. That's exactly what our post-processor confirms our reference machine does. So we can see as we scan through all the different ways of operating our machine, and this will be somewhat laggy because we're using a screen recorder, unfortunately. You can see that I'm changing the waveforms here because I'm scanning through the different ways that we are operating the electrical coils in the reference machine. As we do that, we get different waveforms, different power densities. And our simulating computers have predicted all this using this magnetic software on this screen and animating it. In other words, turning these magnets and watching the machine run inside the computer. So our post-processor here is showing us that the mechanical and electrical energy in the reference machine overlay so precisely that we can't even tell them apart anymore. It only looks like one line. And that happens no matter how we operate the machine. And that's entirely the intended and desired result for a reference machine. We always want the electrical and mechanical energies to match. Therefore, if we use that reference machine to operate some crazy over-unity generator, we know exactly how much mechanical energy we are supplying to that generator. We have literally a readout that will tell us. And we don't have to use some expensive torque sensor to measure it. The reference machine measures it inherently. Not by some expensive instrument or clever design, but inherently in the physics of the machine. That's why I like reference machines so much. They give us a mechanical watt meter that doesn't require a torque sensor. Torque sensors are inaccurate and expensive, difficult to deal with, hard to procure, expensive to calibrate, and generally kind of a nightmare. Until I haven't had a good experience with them. So building a machine that lets us measure it, that's those same quantities in the fundamental physics of the machine, might sound like it's not very important for solving the world's climate and energy concerns. But as to the science of how we do that, it is vital. So our post-processing software here in Excel shows us that it works. And down here on the right, we can see that the energy harvested is always zero. No matter what we do, we've harvested nothing, and that's the point. That's why we call this a reference machine. It is the reference, or the standard, against which other things are measured. It's like a ruler. What comes next is quite proprietary. So, shh, don't tell. And if the camera falls down, it's because the wind is knocking it over. We'll get to that at the end of the video. Here is Sternmotor. I don't often show what I build online. This work is my brand. I do this at a terrible sacrifice, like inventors do. That's why we go crazy and have such a high divorce rate, almost a guaranteed divorce rate. It is very difficult being an inventor in today's American society. There's no support. Compare that to the support given to professional athletes, and it'll bowl you over. So, this is precious to me. Revealing it to you feels risky to me. This is all I have. Can you hear the desperation in my voice? Oh, please, kind sir, do not take it from me. This is Sternmotor. This is one of the original incarnations, following an inspiration that I had for a machine that might be very much unlike a reference machine. In other words, in this machine, we may find that the mechanical and electrical energies do not match, giving us leverage. I went ahead and 3D printed it and assembled it. And we've applied what we've learned recently to modeling it. So now we can model the electrical performance of this machine as much as our computers can do that realistically, which is pretty realistic, especially as we develop that model. Years of research have gone into it. And modeling is never perfect. So it's always an art. There are always limitations, but we can use our computers to run this machine virtually and see what it does. I will show you the results here. These are the results from Sternmotor on the screen. And Sternmotor sucks. It doesn't run well. It's not practical as an over-unity generator or an over-unity motor. It does some pretty amazing things, but they're not sufficient in the practical sense. So I'll illustrate to you why, and we'll try using our camera here. Hello? Yeah, okay. Here's the wireless camera. And I'm just going to use my finger, I guess, to show it. Here in the dotted green line is our copper loss. So if we were going to have copper windings in this machine that would fit and be constructed accurately in terms of representing our model well, this would be the loss level when we run current through our windings. That's the loss in the model. And anytime the machine's output, given by the difference between electric and mechanical energies, that margin that we could take as if it were a profit in a company, anytime it exceeds the amount lost in the copper, you can think of it like profit in a company that has exceeded expenses, or revenue, sorry, that has exceeded expenses and is therefore profit. So we begin to see those in our little jagged lines here. You can see that we turn it on, it exceeds, and all of this is profit. But unfortunately, it's a terrible amount of profit. It wouldn't be a company worth running. For this machine at 100,000 RPMs, which is not practical, which wouldn't work, would completely disintegrate at that speed. At 100,000 RPMs, we could generate less than 1 watt of power. And if we look, we can see that the asymmetry is happening right at a certain portion of the cycle. Between 60 and 90 degrees, we have the widest gap, the widest vertical distance between electrical and mechanical energy. Or if you think of it in terms of money, we have the greatest difference between revenue and expense. At other portions of the cycle, revenue matches expense. There's no profit. It's a reference machine. It's an ordinary electric machine. There's no difference. But in Sternmotor, there are portions of the cycle where we can take an energy profit. They're just small. And so we'd have to wrap this machine out and run it at 100,000 RPMs to even add it up to a watt. That's terrible. It just won't do. Now this is after one analysis. Let's take a look here and I'll show you my trophies. We on? We on here? Okay, let's look at the trophies. This is the trophies. This is the wall of computers that is running our magnetic simulation. I want to give a shout out and a thanks to Dr. David Meeker. Man, I hope I can meet you someday and just shake your hands, because your code is running on all these machines. I have a $3,500 power bill. How did I run up that much of a power bill? By running your code, bro. And it was worth it. I wouldn't be here. I wouldn't be building this stuff if it hadn't been for your freeware, your gift to the world. So I'm always going to give you credit, man, because you deserve it. You did something big and you gave it away. And that, in my world, it's amazing. That is to be human. That is so cool. Anyway. Yeah. So these machines are running all this data, and right now I have 18 of them turned on. So this row of 8 is turned on, this lower row of 8 is turned on, and 2 on the bottom are turned on. That gives us 18 instances, and we divide our 360 degrees of rotation into 18 instances each with 4 cores, and that's how we get this data. It is electrically expensive to do that. I'll show you that I have the windows open and some fans here which are not currently running to partially to get rid of the heat from all the computers. And that's even with not all of them on, but it's summertime, so it's waste heat. I can't use it to heat the house. We'll move on now to the encouraging results, which we've already seen on screen here a little bit. This is our most recent technology called Sternmotor. Now, when I talk about Sternmotor that I just showed our physical and 3D printed version of, Sternmotor wouldn't work in a practical sense, unfortunately. Stern means star in German. Our next motor is Sternmotor. Okay, fine. I gotta name these things something. When I run the Sims, I have to give it a name. Sternmotor. Okay. And here it's showing us that if we run Sternmotor at 15,000 RPM, which is on the high end of the practical range, it's doable. Here you can see that we're generating a predicted 68 watts. That's the maximum generated power. Now, in physical terms, we'll never end up with that much. There will be some more overhead, but we've already deducted our copper winding loss. And we can see in this spreadsheet that dotted green line is up near the 0 on the axis for that information. But if this green line were all the way at the top, it'd be at 0. So we'd have no copper loss. We'd be using superconductors. And I'll tell you, I sure wish we had superconductors. People will be discovering this stuff by accident, I reckon. That was supposed to be a secret. You're not supposed to know how easy it is to generate the technology that changes the world. If we had superconductors, people would be finding it out right and left. Shh. Don't tell. Not yet. We're supposed to be the first. And why? Why are we supposed to be the first? What, just so we make a bunch of money or get famous? Hell no. We're supposed to be the first, so the company that we put around this starts supporting inventors and has the resources to do it. So the people that come after me, come after us all, have the kind of support where we can create stuff like this as a society without killing ourselves in the process. And without just having NFL linebackers get millions, where inventors don't get screwed anymore, where your wife is proud of you instead of living in a different zip code. So there are some encouraging results, and they happen by surprise. And this is the best result so far, showing us that we can get about 60 or 70 watts raw out of a machine that we can literally 3D print and run at an achievable speed. If I move this slider here, but let's try moving it down here and see if it'll render for us. Totally won't. Oh, wow, it's just super duper slow. Okay, I've taken the slider down now to 2300 RPM, you can see here. And at 2300 RPM, we're generating 4 or 6 watts. 2300 RPM is pretty achievable, right? It's slower than most electric motors run in fans or refrigerator compressors. And it's within the range that if we put a little pulley on the axle of one of our machines and a pull string, if we give it a good enough tug, we can get to 2300 RPM. And that means that the machine that we build will generate 4 or 6 watts free for the taking. It'll harvest it from the environment. And that means we can pull start a 3D printed machine that will change the world. Like pull starting a lawnmower. It's possible to make something that we can demonstrate where people can't believe their eyes. Now, this won't be the first time that a machine like that has been made, but it might be the first time that it's been made by people who can actually get that machine used by human beings on planet Earth. What's it worth to be the first if that's not the outcome? Evidently not much. I have to still gas up my car once or twice a week here in 2021. We haven't achieved it yet. We have. But nobody's made a business out of it. And certainly nobody's made a business beyond the profit motive. let's get there. This will be the story of a lifetime. I want to show you a day in the life and the result of doing this, because this stuff doesn't happen for free, right? Neither does this machine. This is a different machine. This one does some really amazing stuff too. We'll talk about that maybe in another video, or maybe no video at all. These are difficult to 3D print. I'll show you this thing. This is supposed to have 0.5 millimeter little holes in it. And the printer made it okay. Even working slowly, it took like 5 hours, but I still couldn't use it. Making these things takes a lot of time and effort, right? Here's a failed print. Okay, there goes $4 worth of filament out of my paycheck. Another day, another $1. And that's for a machine that the computers end up saying wouldn't work that well anyway. This is a heck of a job, and it's way more than a hobby can sustain, right? We'll take a look at one of our test stands down here. It's a little bit goofy looking right now, for sure. But as we go into detail about these things, you can see that this is well beyond like stamp collecting, model rocketry, or bowling, or something that I would do on my spare time. Right? This isn't gun collecting. This is like an all-consuming thing where you can look at the amount of time invested into getting all this stuff done and right, and making these all by hand, and programming the it goes on and on and on. And it goes on and on and on because I'm not an NFL linebacker. If I was, I'd have a coach. I'd have $1 million, and I could do this work so much faster. The biggest limitation right now that I'll tell you, and you'd see this in your life too, if you were mining Bitcoin or making, energy harvesting or whatever, if you had to use a lot of computers, it gets really expensive. Now I find I got really good leverage in buying the computer hardware and tuning it. So my personal investment in buying all these computers was possible for me. I'm not sure if this shows up very well for you here, but you can get an idea of what the cost must be just by looking at all these wires, right? And this room used to be my master bedroom back when I had a family in this house, but let it not be lost on us that working as an inventor dedicated to something, the more you study history of the people who have done this, the more you will see story after story of personal difficulty. And that's to be expected. There's going to be a lot of pressure when we finish this technology to make a profit from it, right? There are going to be a lot of people wanting to get around our IP portfolio so that they can start their own companies and make their own products. That's all fine and well. But those motives exist within the framework of a society that does things for profit. And that's why our world is kind of messed up right now. It's very polluted. We have problems like climate change that the profit incentive cannot solve. And they're killing us. Or they might. And it's sort of irresponsible to even run that risk. I got kids, man. Sorry, the generations that came before you might have screwed it all up, but make sure you do your homework today. Mow the lawn. Oh, okay, boomer. Right. You can see where that angst comes from. So we're going to do something where we can support other inventors. That will be radical. Maybe it doesn't sound radical, but find me one company that does that and does that well, so that those of us who do invent feel like they have an ally, feel like it's a seller's market. Right now in the housing market, it's a seller's market. If you're lucky enough to own a house, you set the terms. It's a seller's market. Imagine that being possible for people who play football, right? It already is. If you're really good at playing ball, man, you got an agent, you can pick your team, and you can negotiate your rates because you are good. You're good, and you should be able to do that because you're good. You're irreplaceable. You're one of the best. That's what I want to do for inventors, and we're going to use this technology not only to help change climate change, to help irrigate deserts, to help desalinate the ocean, to help pump excess heat off this planet and solve our big problems. We're also going to help the people that spend their lives generating and creating these kinds of solutions. Just like the NFL, just like the people out there who are already in that model. We're going to include inventors now because the world needs it and the money is there. It's just nobody's done it yet. We're pioneers. So let's take a look. This is where the master bed was. And I moved that last night. It's all kinds of dust. You can see we wasn't like neat freaks or anything like that. Here's the plug. So this is running those solvers right now through some pretty heavy wire and like a 3-phase connector. And that goes back into the 240 dryer outlet. So if we go to the Natty dryer back here, take a look behind it, you'll see we've tapped into that, and that's where the electricity comes from to run all these computers, because if I have it running out of the wall socket, that's just not a happening thing. They keep tripping breakers, and then it's all wasted because the data goes away and we have to restart. This is the cost. This is the cost of making those machines, at least to me. That's me cleaning up this house. That's why it's so important to support people who invent. That's why it's my personal mission, because this is the second time that I've had to deal with my own family imploding because I'm too busy making something that I want to be able to change the world. I see climate change. I experience climate change. My heart breaks when ashes fall from the sky. When I hear the old timers say, man, this is like the new normal. It wasn't this way when I grew up. Yeah, no joke. I believe that. It wasn't this way when you grew up. And if I've even got a slight chance, but a non-zero chance, if I've got a slight chance of helping change that, how can I stand idly by and not try? I have to. So that makes me an inventor. But I'm not the only one. There are plenty of people who are trying to do this. So far, I'm the only one who is sharing the gory details of my personal life and some very privileged inner data that has come to me at great personal expense. But think about it. Okay, so somebody steals the technology. I'm another ripped off inventor. Yeah, what's new? Okay, maybe the world still gets the technology and I die in a cardboard box. Is that a win? Yeah, for everybody but me, it's a win. Deal. Last item, here's the 3D printer getting worked on. We got space for a webcam using a Repetier server. I bought some cheap LED strips that go on there. And back here is our rack where we've got all kinds of good carbon fiber nylon. And that's how we will get a 3D printed rotor that may actually be able to hack 15,000 RPM. May God bless the future, where those who create are valued and supported by at least one company with the means and the ethos to value them and support them. Let's not just end climate change. That's already happening. But in the longer sense, let's end this problem of the screwed, crazy inventor. These people are heroes. They're just as much heroes as Kobe Bryant. They are heroes. Let's support them. That's my goal. I hope you climb on board. We'll see you next time.